Hi everyone, welcome to the data channel. So here we are bringing up a next set of video that is as part of the system design series. We are bringing talking about data engineering. So we are bringing up one of the critical pillars of data engineering, we would say, when you're talking about the system design, that is scalability. So as a data engineers, we aren't just moving the data around. We are not just like integrating different systems, complex systems, and thinking of data quality, etc. But we are also building pipelines, systems, and architecture that must handle the data volume, data growth, sudden spikes in the volume, right? And also the evolving workload. So constantly evolving workload because the data is not like once you put into production, it is not just the volumetric wise, it might not be constant as we are looking, right? So over the period of time, the data might increase, the volumetric growth might increase, or even there might be sudden spikes in the data, which can be very it might be very dangerous on the system itself when the spikes are coming up, right? So that is where it is not just building the systems which are integrating different systems and making it having data quality checks, auditable, alerting, etc. So these along with that, this concept called scalability is also very important. So without without breaking the systems, and the pipeline should be maintained, even the data volumetric growths are changing, volumetric like parameters are growing, right? So in this video, we will explore that part of concept of scalability and how that really means for data engineers and the different scaling strategies, and what are the challenges and real world case studies and best practices for the future-proof data platform. So stick around till end of the video because I'll be able to share some insights based on the experience here. So that will definitely help you understand the concept in detail and yet keeping it simple. So if you're new to this channel, we would recommend you to please subscribe and also press bell button for instant notifications. So let's get started. So this is a high-level topics that we'll be covering. What exactly the scalability means for data engineering. What is the difference between horizontal and vertical scaling? Where scaling matters in data engineering really, and what are the challenges? Some challenges you can think of in scalability, and also we'll take a Netflix as a case study and see how they've implemented basically the scalability and how they enable the scalability. And also we'll see some of the best practices for building scalable data engineering pipelines. So first of all, we'll see why scalability matters for data engineers. So scalability, you might be know, I mean, it's basically the definition of scalability is you want to kind of increase or upscale or downscale. So scalability is not just upscaling, so it should automatically also downscale. So there is upscale and downscale, right? So you can increase the infrastructure, right? You can increase the memory, you can increase the CPU, you might increase the networking capability, IOs, right? So the scalability has different parameters. It is not just about increasing the speed of a server, right? It might have a combination of CPU, GPUs, actual memory, physical memory, and also it depends on like whether you are using a some places you might be using GPUs, right, and graphical related information, so processing. So there you need more graphical powers to compute that, and in some cases where you need a network IOs, so you need to increase that network IO and network bandwidth. So the scalability has different paradigms basically. But end of the day, what scalability means is you need to build a system which is kind of adjust to the unprecedented volume that might come up in the future or near future. So that way, if you're building your system, so that makes the system more reliable for the customers, even there is a sudden spikes in volume or dips in volume. So no matter what, the pipelines, the data engineering pipelines will still have the better performance to meet the KPIs and the SLAs basically, right? So that is where the scalability matters, okay, and what that is what the scalability means, right? And so one question here is, can your system handle growth without without performance issues? So for the data engineers, this growth could mean like as I was, it might be a data volume growth. Maybe the data might suddenly grow from a couple of GBs to TBs and petabytes, and also the data velocity. So the data velocity also keeps changing. The streaming millions of records per second. So that might start coming up from millions to say 10 millions, etc. And also the variety of the data. So because the processing the structured data versus unstructured data is like a lot of difference will be there, and the compute difference also will be there. So basically that is another thing, and also the more users. So you might introduce more users, like maybe the users of data analyst, data scientist, and the dashboards so that people are using and connecting to the your data. So might suddenly increase, right? So it might be at any level, right? As I said, it might be data increase, it might be velocity, it might be variety, or it might be even the number of users who are using the system might increase over the period of time. So that is where, as a senior level data engineer or architect level, so there is one concept that is called a data volumetric growth analysis. So before you deploy something, any code into production, you need to be aware of how the system can sustain at least 5 to 6 years, or like 8 to 10 years down the line. You need to have that visibility, and you need to have some calculation around these parameters. What would be my volume? What would be my velocity, variety, users, etc. Again, it is like it depends on like how you want to analyze that. You can take historical data and analyze. You can even look for the business growth, how business is growing over the period of time, and you can even connect with the business and understand what more they are expecting from this, and what more data we can expect, right? So based on that, you can conclude. So approximately this is the volume of data that might come over a period of time. So these are all the parameters: volume, velocity, variety, and users, right? And ultimately, if your pipeline performs well with 10 GB, but crashes at 1 TB of data, so it is not scalable, right? So if your query runs and returns the results in 2 seconds today, but actually in 2 minutes after data doubles, it is not scalable. So scalability is about designing the system that grows gracefully with load. So that's quite important, right? So the pipeline should not have that hindrance. So automatically the thing should be scalable. That means you're talking about auto scaling here. When you talk about a gracefully, like working without any issues, that means in the behind the scenes that we have enabled auto scaling, where it automatically adds the number of nodes, increase the GPUs, CPUs, and again like downscale automatically, right? So that is what we need to think about auto scaling here. So these are the kind of things where it will definitely matter. So without scalability, you will definitely cannot meet the business SLAs, and you might lose the business stakeholders' confidence. There might be pipeline failures, and it might impact the business revenue as well, right? So that ultimately it boils down to that. So now we will see the difference between horizontal and vertical scaling, but first we will see what is vertical scaling. So vertical scaling is quite simple, right? So what you're doing is you're adding more. You have a disk, so it is currently you're using for the project. It might be cloud infrastructure, cloud VM, or it might be on-premise VM, virtual machine. So if you want to add more CPUs, RAM, or disk to a single machine, so you're not increasing the number of machines. You are making the existing machine more powerful by adding the additional hardware, additional networking, etc. Right? So that is the what we call as a vertical scaling. So existing system, existing server, you are making it more powerful, right? And it works well for maybe smaller systems, but it has a limit because hardware cost is like skyrockets when you are talking about increasing it vertically, right? Because a single point of failure might be really a disaster. Like you cannot go on increasing it. So there is certain limit you can set for increasing our horizontal scaling, but definitely it has a hardware limit, and it becomes quite expensive once it reaches certain limit. And but definitely when you are using like you're building a small POCs or you're doing MVPs, right? So and in that cases you can still use the concept of vertical scaling, and you can extend, or you can like you can do a vertical scaling by adding the CPU, RAM, disk, etc. So this is vertical scaling, right? So there is a same server, you're increasing the capacity of that server. So now on the contradictory on the other side, contrary on the other side. So horizontal scaling is what we call it as a scale out. So previously vertical, what we are calling is a scale up. That means we are going up. That means we are increasing the capacity of the server. Now horizontal scaling is nothing but we are scaling out. That means we are it is like a extending the number of nodes. So that is why it is like vertical and horizontal. Horizontal means you are now go on adding the number of nodes here. That's why it's scaling out. And like it basically you're adding more machines here. So the number of machines are getting increased or the number of nodes are increasing, and you're enabling the concept of distributed computing here. That means you're distributing the load across different machines by adding more machines. So this is a most preferred strategy in the modern data engineering, and especially with the distributed systems like Spark, Kafka, Snowflake, and cloud native warehouses. Because Spark, the major architecture or the main architecture, the core behind the architecture of the Spark is distributed computing, right? So if you cannot horizontally scale systems, right, you cannot make the best utilization of the Spark. So that is why even though you are using Spark, so Spark architecture works well with the horizontal scaling. That means you need to keep on adding the number of nodes, which Spark call it as a worker nodes, right? So that is where the you can leverage the modern data engineering like paradigms or the technologies with the horizontal scaling. So, for example, you instead of running a Spark jobs on one big server, so run them in a say cluster of 50 commodity servers, right? So that makes it much faster, cheaper, and also it leverages the capacity or capability of the Spark to the extent because Spark is built for that. So, and most of the big systems or the big data processing systems, etc. Right. So all are built on the distributed systems. So that is why the horizontal scaling is what we call the scalability for the day. That means it is very relevant for today. And yeah, and if you're using Azure, AWS, Databricks, Google GCP, right, all these managed services, so they provide all of these horizontal servers, which make things auto scaling. That means you can configure your servers, saying that like I need minimum 5 workers, and it can extend till 8 workers. So it start with 5 worker nodes, and it automatically scales to 8 workers during that. Where there is a volumetric spike or a processing spike your pipelines need more CPUs. So in that case, it automatically scales or adds up that three more additional nodes into the processing, and again scales down when it is not necessary, right? So that is where we will be using that way you are actually increasing the processing speed and also keeping the cost in check because you are enable the auto scaling, right? So it is like scales up and scale down automatically. So that makes it more convenient, more cost wise. Also, it is more cost friendly, and also you are leveraging the capability of distributed computing. So that's about vertical and horizontal scaling, right? And now if you see the scalability dimension, so it has different dimensions as I was speaking, right? So it is scalability is not just about increasing memory or CPU. So it has different thought process. You can think of scalability from different different paradigms. For example, if you talk about storage scaling, right? So storage scaling, like if you are partitioning by number of users, graphical and tiered storage, whether you're using hot versus cold storage, and you are using data lakes, lake houses. So that those are actually mostly like scalable almost to infinite with the cloud storage. And you can use partitioning, bucketing, and clustering to ensure the performance and the performance scales too, not only just the infra behind it. And when you talk about processing scaling, so you can say you are using the Spark jobs example, right? So Spark, Databricks, Flink, and you're using Kafka streaming, structured streaming, where you are working on the processing the streaming data. So these frameworks allow adding more executors or the worker nodes to the scale computing. And also you can scale the streaming. Streaming scaling is nothing but again, it is like where you're using Kafka, Kinesis, PubSub, or like these like publisher subscriber models where you're building. So you can horizontally scale the systems, and that makes the streaming systems more scalable. And you can like can your pipeline handle say for example 10 events per second today and scale up to the like 100K events per second tomorrow. So these kind of questions we need to ask and build the systems, right? And in streaming also, it becomes very important scalability, because streaming is a little tricky when it comes to the performance, because sometimes the data will suddenly flow, suddenly bumps up, and we don't have the control, much of a control over it. And any failures in the streaming would be quite dangerous, because once the streaming fails, the backfilling the data will become very challenging task. So when you're talking about when you're building a streaming systems, we need to really be concentrating about scalability. We need to build, you need to perform a lot of performance testing before you deploy the code to production and the infra to the production. So that is, I think this is one of the important aspect you need to consider when you're working on the streaming data. And query scaling. So query scaling also it might happen, right? Suppose you are building a distributed SQL query engines, right? And you might be using BigQuery, Redshift, like scale elastically based on the workloads. And also you might be scaling compute clusters, ensuring data analysts don't suffer the sometimes the queries might slow down. And along with this, you can even think about, apart from these four, you can think of like APIs and server layers when you're exposing data through the APIs. So there will be load balancer, caching, ensure high throughput. So without scalability, what happens is even 2x increase in the user traffic can choke at the entire system. So to avoid this choking of the entire system, so that is where you need to consider all of these aspects, all of these dimensions of scalability, and understand you need to question: is my storage scalable? Is my compute scalable? Is my processing pipeline scalable? Right, and even my the interacting interfaces like APIs are able to handle the scale that might like we might see in the future, right? So these are the very important other dimensions you need to think of when you're talking about scalability. So next, what are the challenges in scalability? So first is like you can think of data skew. So some partitions hold more data than others. So there are modern techniques to handle this. So if the data is skewed and you are partitioned, there is something called as liquid clustering. So technologies are there, but even the technologies that are there, the fundamentals remains the same. So you need to keep a check on whether any partitions is becoming a hard partition, whether the data is getting skewed in one particular partition. And because partitioning is more commonly used when you're working on big data systems, right? And other is a network bottleneck. So more nodes means more number of shuffling data transfer will happen. So distributed computing definitely has one of the challenge, right? So that is like more number of nodes you are adding, like you are increasing the number of nodes and you are scaling horizontally. That means definitely there will be a lot of data shuffles, network input output operations are happening. So that is where you need to take care of the shuffling and data transfer, and what is the speed, whether it is. So you need to keep a check of about this health of this traffic basically. And also the cost explosion. So scaling compute horizontally, like the cloud vendors or the managed services are like charging hefty money for that, right? So because the so once you are in managed services cloud, right? So you are scaling it up horizontally, but again, so it might to have a limit. It might to we need to have a cost check. So because every project has a budget, every project runs comes up with the constraint of a budget. So it is not be unlimited cost, right? So you need to see what exactly how much you can scale, how much like scalability you can afford considering the project budget, etc. Right? And also the operational complexity. So because definitely there will be more number of nodes means you need to perform more monitoring and failure handling and orchestration. So luckily, most of these are now in the cloud, Azure, AWS, and GCP. So it is like become a managed services. But still, as a if you are in operations, data engineering operations, if you are kind of monitoring the systems very closely, so definitely still you need to kind of get these logs, keep on analyzing and build a dashboards and check the health of these nodes constantly. So as a senior engineer or the data engineer, you are expected to balance the performance, cost, and operational simplicity. So that is why it is very key to kind of understand the scalability from different dimensions and what would be the challenges out of it, right? So next we will move and see about the real time. We'll take a case study here. So let's this practical case study where we are talking about real time recommendation engine. So, right. We can talk about a Netflix as an example, right? So they handle billions of events per day from streaming activities, device logs, and the user interactions. So data basically they will be ingesting using Scala, the Kafka, and the data processing they use Spark, Scala, and like on AWS. And the storage for the storage they will be using S3, which is Amazon-based storage system, and which they create as a data lake. And finally, they have the personalized recommendation engine, which will be served via horizontal scalable APIs. Their architecture proves that every layer must be scale independent, like whether it is an ingestion layer, storage layer, processing layer, or like serving layer. So all the layers should be scalable. So that is the key here, right? So that is the use case that we can take and see how Netflix has built their system, which at a ingestion layer is having a Kafka, which is scalable system, and data processing layer. So once the ingestion happens, you need to process the data. That is also scalable. And again, when you're serving the data or storing the data into the S3, that is also scalable. And finally, you have something called you need to run some personalization engines, etc., and show that personalized recommendation to the customer. So that is also real time, and also it's more scalable. So even though the traffic increases or decreases, the customers or the end users should not feel that hindrance, right? So the personal recommendation should be like near real time. So that is where it's quite important to understand and see how enterprises have built the scalable system. Scalability is not just about building a pipeline, scalable pipeline, but it is end-to-end use cases, understanding all the dimensions what we discussed. So now we'll go to the advanced scalability strategies. So you talk about like micro batch. So now we'll talk about the advanced scalability strategies. So like one is micro batching. Micro batching means use micro batching for semi real time to balance the cost and throughput. Like instead of having the pipelines real time, what you can break that real time pipelines into a maybe like 10 minutes or 15 minutes interval, which we call it as a micro batching. So that way you can save some cost and you can still make the system scalable, right? And data skew mitigation. So when you need to apply the data skew mitigations like salting, repartition, and liquid clustering, all these techniques are there to kind of handle this data skew issues. And auto scaling with guardrails. So this is like you guardrails means you are not auto scaling without any limit, right? So there should be certain limit considering the cost, considering the budget of the project, etc. So you need to set that minimum and maximum cluster size to control the cost. So that is some calculation you need to perform when it is going from 5 workers to like say 8 worker or 10 worker. What is the maximum number of duration it is going, and what is the cost that we are paying? So that you can also monitor the cost over the period of time, and you can keep on fine tuning that min and max cluster size. And you have a data pruning and compaction. So to reduce the overhead in data lakes, so you need to keep on data pruning, and also you need to keep on compressing the data to reduce the number of like to keep the cost in check, storage cost in check. And you have a global and regional scaling. That means like if you have multi-region data pipelines designs, so you can have either global or regional. So it depends on the customers whether you are dealing with, right? So suppose if you are building a system which is serving parallelly to the global customers, so then you can host that all the worker or the nodes to the different locations, and you can replicate the data so that the data sits near to them, and it will be faster for them and more scalable. But if the customers are concentrated on a particular region, so then you can host only the processing engine or the data near to that region or in that region, so that the accessing cost and the processing cost and the user's consumption will be much faster and more scalable. So with that, we will see what are the certain best practices you can think when you're talking about scalability, like, right? And so first is the design stateless components. That means it should be easier to scale horizontally. So you are thinking that aspect in the first when you're building as architect, you're building the system, right? So you need to keep that space so that your system can scale horizontally if it is required. You might be not building it for today, but if you want to have that provision for tomorrow, your system should be able to handle the horizontal scaling. And also the partitioning and the parallelism, right? So you need to have that, you need to partition the data, like you need to think about like balancing the load across. Okay. And observability. So you need to keep on like monitoring throughput, latency, and cost, etc. And also you can have you can leverage the cloud native elasticity, but also monitor the billing very closely. Okay, because auto scaling will can be disastrous if it is not monitored. The billings are monitored very closely, and also you need to test for a different scale. That means you need to test with a different load, run the load test, performance test with synthetic data and synthetic load to before you deploy the code into production, so that you can measure what your system is capable of once you deploy this into production. So you are making sure the design that we thought about scalability, whether it's working or not. So if you do that kind of performance testing or load tests. So with that, we will see we'll come to the end of the video. So this is like that's scalability in data engineering, right? And we explored what it means, scalability strategies, real world examples, challenges, and best practices. So one thing to remember is, as a data engineer, your job is not just to build pipelines, but to make them future proof for and especially for the any scale that might come up in the near future. So if you find found this video useful, and if you have any comments or suggestion, please comment in the comment section, and also hit like and also subscribe for this channel. Thanks for watching.